Let's get ready to explore. Number 10. The signal from nowhere. In March 2003, a signal emerged from the data collected by the Arecibo radio telescope in Puerto Rico, flagged not by a professional astronomer, but by millions of ordinary computers running a screensaver. The SETI at Home project, which distributed chunks of Arecibo's sky survey data to volunteers around the world, had found something it couldn't explain. The signal was designated SHGB02+14A, and it was unlike anything else in the catalog. The SETI at Home project was, at its core, a needle in a haystack operation. Every day it generated 15 million signal reports, the overwhelming majority of which turned out to be noise, interference, or known astronomical phenomena. Researchers at the University of California, Berkeley had developed precise criteria for what a genuine extraterrestrial signal might look like, and most candidates failed within seconds of scrutiny. SHGB02+14A did not fail. The signal appeared at approximately 1,420 MHz, one of the frequencies at which hydrogen absorbs and emits energy. This is significant because SETI researchers have long theorized that any civilization attempting to broadcast its existence would use this frequency, a kind of universal calling card written into the physics of the cosmos. The signal was observed on 3 separate occasions, for a total of around 1 minute, and it originated from a point in the sky between the constellations Pisces and Aries, where no known stars exist within 1,000 light years. Dan Wertheimer, chief scientist for SETI at Home at UC Berkeley, described it as the most interesting signal the project had ever produced. The team was careful not to overclaim. The signal was weak, and its unusual drift rate raised as many questions as it answered. When researchers deliberately pointed Arecibo at 200 of their best signal candidates in February 2003, everyone disappeared on closer inspection except SHGB02+14A, which grew stronger. The signal has never been fully explained, and it has never resolved into anything definitive. It came from a region of sky conspicuously empty of stars, at a frequency conspicuously associated with life-bearing chemistry. Whether it was noise, a natural phenomenon of a previously unknown kind, or something else entirely, nobody has been able to say with certainty. Number 9. The first flash. On July 24, 2001, something in deep space released a burst of radio energy so violent and so brief that it would sit unnoticed in an archive for 6 years before anyone realized what they were looking at. It was detected by the Parkes Radio Telescope in New South Wales, Australia, and it would later be named after the man who found it, West Virginia University astronomer Duncan Lorimer. The Lorimer burst changed astronomy forever. At the time the data was recorded, nobody was looking for anything like it. The Parkes telescope was conducting a pulsar survey of the sky near the Small Magellanic Cloud, cataloging the regular, predictable pulses of rotating neutron stars. Fast radio bursts, as a category of astronomical event, did not yet exist. There was no framework, no terminology, no expectation that the universe was capable of producing what Lorimer's student David Narkovich found when he sat down to reanalyze that archival data in 2007. The burst lasted less than 5 milliseconds. In that fraction of a second, it released more energy than our sun produces in several days. Its dispersion measure, the way radio waves of different frequencies were delayed by the ionized gas between the source and Earth, measured 375 parsecs per cubic centimeter, placing the source well beyond the Milky Way, potentially billions of light years away. Nothing in our galaxy, and nothing in any known astrophysical model at the time, was supposed to do this. Lorimer published the discovery in the journal Science in 2007, and the response from the astronomical community was deep skepticism. Many researchers suspected instrument error, local interference, or some mundane terrestrial cause. It took years of subsequent detections from multiple telescopes around the world to establish that fast radio bursts were real. that the cosmos was producing them constantly, and that we had no credible explanation for their origin. The Lorimer burst remains one of the brightest fast radio bursts ever detected, and its source has never been identified. It was a 5-millisecond message from the deep universe, received by accident, understood by no one, and we have been trying to decode it ever since. Number 8. The Repeater. In November 2012, a fast radio burst arrived at the Arecibo Observatory in Puerto Rico from a direction nobody had been specifically watching, catalogued as FRB1211102 and filed alongside the growing list of one-time cosmic flashes that astronomers were struggling to explain. Then, in 2015, it came back. Researchers pointed Arecibo at the same coordinates and caught it firing again and again. The universe, it turned out, had something to say more than once. The significance of a repeating fast radio burst cannot be overstated. Every theoretical model built to explain FRBs in the years following the Lorimer burst assumed a cataclysmic one-time event. Colliding neutron stars, evaporating black holes, catastrophic stellar explosions. These were death events. They happened once, violently, and left nothing behind capable of repeating. FRB121102 did not fit any of these models, and its repetition forced astronomers to tear up years of theoretical work and begin again. By 2016, the Very Large Array Radio Telescope in New Mexico had pinpointed the source to a dwarf galaxy approximately 3 billion light-years away in the constellation Auriga, making it the first fast radio burst to be localized to a host galaxy. Hundreds of bursts have now been detected from this single source. In 2020, researchers identified an approximately 157-day activity cycle, periods of frantic bursting followed by relative silence, suggesting something orbital or rotational was governing the emission. No known astrophysical object produces this specific combination of behavior. The associated persistent radio source at the same location, a faint but constant glow of radio emission between bursts, deepens the mystery further. It implies a complex, energetic local environment that no current model fully accounts for. Proposed explanations include a precessing magnetar, a neutron star in an extreme binary system, and processes involving the magnetic field geometry of compact objects in ways we don't yet understand. Something 3 billion light-years away has been firing radio bursts on a schedule, from a location wrapped in persistent radio light in a galaxy barely 1% the mass of the Milky Way. The universe doesn't usually keep appointments, and we still don't know who set this one. Number 7. The Galactic Center Phantom. Between September 30th and October 1st, 2002, the Very Large Array Radio Telescope in New Mexico was conducting routine observations of the central region of our galaxy when it recorded something that had no business being there. 5 bursts of radio energy, each lasting approximately 10 minutes, each arriving with clockwork regularity every 77 minutes, emerged from a point roughly 1.25 degrees south of the galactic center. Astronomer Scott Hyman and his colleagues at Sweetbriar College and the Naval Research Laboratory published the discovery in the journal Nature in 2005. They gave the source a designation, GCR-TJ 174-5-3009. The Milky Way's central region is one of the most energetically complex environments in the known universe, crowded with pulsars, magnetars, supernova remnants, and the gravitational influence of the supermassive black hole Sagittarius A star. Against this chaotic backdrop, radio transients appear and vanish regularly, but they don't behave like GCR-TJ 1745-3009. Pulsars pulse in milliseconds or seconds. Known radio transients flare unpredictably. Nothing in the galactic center was supposed to emit regular 10-minute bursts on a 77-minute cycle. The 5 bursts detected in 2002 were of equal brightness, at a frequency of 330 megahertz. A faint additional burst was recovered from 2003 archival data, and a weaker, shorter detection followed in 2004 before the source went effectively silent. The brightness temperature of the emission, greater than 10 to the 12th power Kelvin, if the source is beyond 70 parsecs, requires a coherent emission process, unlike almost anything previously catalogued. Models proposed to explain it include a nulling pulsar, a pair of orbiting neutron stars, a precessing radio pulsar, and a transient white dwarf. None fits comfortably. The distance to GCRTJ 1745-3009 remains unconstrained. No optical, infrared, or X-ray counterpart has ever been identified. Despite dedicated monitoring campaigns with the VLA and the Giant Meter Wave Radio Telescope in India, the source has produced no confirmed detections since those early observations. It broadcast its peculiar rhythm for a few months in 2002, hinted at a repeat in 2003, faded in 2004, and then went silent. Something in the direction of our galaxy's own center fired 5 equal bursts on a 77-minute schedule, then stopped. No known class of object matches this behavior. Whatever it was, it has not spoken since, and we have no idea what kind of object produces a pattern that precise and then simply disappears. Number 6. The WOW signal. On August 15th, 1977, astronomer Jerry Amon was reviewing data printouts from Ohio State University's Big Ear radio telescope when he encountered a sequence of characters so far outside the expected range that he picked up a red pen and wrote a single word in the margin. That word was WOW. The signal had arrived the previous evening, and in the 72 seconds it lasted, which was the maximum time Big Ear could observe any fixed point in the sky, it registered as the strongest, most precisely structured radio signal ever recorded from beyond our solar system. Big Ear was part of a SETI survey of the sky, scanning for exactly the kind of transmission scientists had theorized an intelligent civilization might broadcast. Researchers had long speculated that any civilization attempting to make contact would transmit at 1,420 megahertz, the emission frequency of neutral hydrogen, the most abundant element in the universe. The logic was elegant. Any spacefaring civilization would know this frequency, and choosing it would signal intent. The WOW signal arrived at almost exactly 1,420 megahertz. It was approximately 30 times stronger than the background noise of the sky, a staggering intensity for a signal of unknown origin. Its apparent source was the constellation Sagittarius, near the star group Chi Sagittarii. It was narrowband, focused, non-repeating, and bore every characteristic that SETI researchers had theoretically predicted an intentional interstellar transmission would possess. It showed no signs of Earth-based interference. It matched no known natural astronomical phenomenon. Despite hundreds of follow-up searches over the decades, using increasingly sensitive equipment, the signal has never been detected again. In 2017, astronomer Antonio Paris proposed that the signal might have been caused by 2 passing comets. But this hypothesis was widely rejected by researchers who noted that comets do not emit strong narrowband radio signals at precisely 1,420 megahertz. The WOW signal remains, after nearly half a century of searching, completely unexplained. For 72 seconds, something in the direction of Sagittarius broadcast at the exact frequency scientists had designated as the universal calling card, and then never spoke again. It matched every prediction we had made about what contact would look like. Whatever produced it has remained silent for 47 years. Number 5. The clocks that changed their minds. In 1967, Cambridge graduate student Jocelyn Bell Burnell discovered pulsars, and astronomers quickly recognized them as among the most precise natural timekeepers in the universe. These rotating neutron stars emit beams of radio waves that sweep Earth with metronomic regularity, some spinning hundreds of times per second, their timing so reliable that physicists use them to test general relativity. The assumption built into every model of pulsar behavior was that their emission, however complex, would be stable and predictable. Then researchers began to find pulsars that were doing something else entirely. The phenomenon is called mode switching, and its existence is deeply unsettling for pulsar physics. In mode-switching pulsars, the radio emission abruptly changes character in a matter of seconds, flipping between distinct emission profiles that are internally stable but externally inexplicable. The switch is not gradual. It is not triggered by any detectable external event. The pulsar simply decides, on a timescale of seconds, to emit in an entirely different way. The case of PSR B0943+10 crystallized the problem. In 2013, a research team published findings in the journal Science, demonstrating that this pulsar simultaneously switches between two states, one in which it is radio bright and X-ray faint, and another in which it is radio faint and X-ray bright. The transitions happen in seconds and affect the entire magnetosphere of the neutron star at once. This is not a localized twitch in the emission region. It is a global reorganization of the electromagnetic environment surrounding the entire star, happening faster than any known physical mechanism can travel across the object. Theorists have proposed explanations involving changes in plasma flow through the pulsar's magnetic field, abrupt shifts in current patterns within the magnetosphere, and coupled instabilities between the stellar surface and the surrounding environment. None of these models fully accounts for the simultaneity of the radio and X-ray transition, or for the fact that dozens of pulsars across the galaxy display the same behavior in ways that suggest a common underlying mechanism we simply haven't identified. If the universe's most precise natural clocks are spontaneously reorganizing their entire electromagnetic structure on a timescale of seconds, and our best physical models cannot explain why, it suggests there is a fundamental gap in our understanding of how matter behaves under the most extreme conditions in the cosmos. Number 4. The bruise on the sky. Embedded in the oldest light in the universe, the cosmic microwave background radiation left over from the Big Bang itself, there is a region that should not exist. It was first identified using data from NASA's WMAP satellite in the early 2000s and confirmed repeatedly by the European Space Agency's Planck satellite in subsequent years. Located in the constellation Eridanus, it is a roughly circular patch of sky measurably, consistently, and significantly colder than everything around it, approximately 70 microkelvin below the surrounding average. Cosmologists call it the CMB cold spot, and it has resisted explanation for more than 2 decades. The cosmic microwave background is the universe's baby photograph, a near-perfectly uniform map of the temperature fluctuations that existed 380,000 years after the Big Bang. Small temperature variations were expected and predicted. They are the seeds from which galaxies and galaxy clusters eventually grew. But the cold spot is not a small variation. It is anomalously large, anomalously cold, and anomalously circular in a way that sits at the extreme edge of what standard cosmological models predict should be possible by chance. In 2015, astronomer Istvan Chaput of the University of Hawaii and his colleagues confirmed the existence of a supervoid in the same direction, a region of space spanning roughly 1.8 billion light-years, containing far less matter than the surrounding universe. Voids can cool the microwave background slightly as photons lose energy passing through them, and this discovery initially seemed to close the case. It did not. When researchers calculated how much cooling the supervoid could produce, it accounted for only a fraction of the measured temperature difference. A significant residual anomaly remained, and remains still. University of North Carolina physicist Laura Mersini Houghton and other researchers have proposed that the cold spot could be the imprint of a collision with a neighboring universe, the gravitational bruise left when our cosmos brushed against another bubble of spacetime in an inflationary multiverse. Most cosmologists consider this hypothesis speculative. They also cannot explain the cold spot without it. Is the coldest, emptiest, most perfectly circular anomaly in the observable universe simply a statistical accident? Or are we looking at the scar left by a collision with another universe entirely? Number 3. The particle that broke physics. On the night of October 15th, 1991, an experiment called the Fly's Eye, operated by the University of Utah at the Dugway Proving Ground in the desert west of Salt Lake City, detected the air shower produced when a single subatomic particle slammed into the upper atmosphere. The researchers worked backward through the data to calculate the properties of the particle that had caused it. Then they checked their mathematics again. And again. The energy they measured was 3.2 times 10 to the 20th electron volts, 320 exaelectron volts, an amount so far beyond anything previously recorded that the physicists involved named it the "oh my god" particle. The speed of this particle, if it was a proton, was 99.999999999999999999999999999 1% of the speed of light. In a year-long race with a beam of light, it would have lost by mere thousandths of a hair. Its energy was approximately 40 million times greater than the most energetic protons ever produced by the Large Hadron Collider, the most powerful particle accelerator humans have ever built. It carried the kinetic energy of a baseball thrown at moderate speed, concentrated into a single subatomic particle, traveling from the deep universe to our atmosphere. The problem is not simply that this particle was extraordinarily energetic. The problem is that it should not have been able to arrive here at that energy. In 1966, physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin independently calculated a theoretical maximum energy for cosmic ray protons traveling long distances through space. As protons travel through the universe, they interact with photons in the cosmic microwave background, losing energy continuously. Any proton traveling more than roughly 160 million light-years should arrive with less than 60 exaelectron volts. The "oh my god" particle arrived with more than 5 times that limit. When astronomers traced its trajectory back through the sky to find what had accelerated it, they found nothing. No known astrophysical object in the relevant direction, no active galactic nucleus, no gamma-ray burst source, no neutron star binary capable of producing energies anywhere near this scale. The telescope array in Utah and the Pierre Auger Observatory in Argentina have since detected dozens of additional ultra-high energy cosmic rays, confirming the Fly's Eye result was not an error. The source of these particles remains unknown. A particle arrived from space, moving so fast that, from its own perspective, the entire 13.8 billion year history of the universe had elapsed in a fraction of a second. We still have no idea what fired it. Number 2. The signal from our own backyard. On April 28, 2020, 2 independent teams of radio astronomers detected something that the entire field of fast radio burst research had assumed was impossible. The Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, and the Survey for Transient Astronomical Radio Emission 2, known as STARE-2, simultaneously detected a fast radio burst from inside our own Milky Way galaxy. The source was a magnetar called SGR 1935 plus 2154, located roughly 30,000 light-years away in the constellation Vulpecula, originally discovered in 2014 by NASA's Swift Observatory. The burst, designated FRB 200428, was accompanied by a powerful X-ray flare. For the first time in the history of the field, a fast radio burst had a face. The significance of this detection was enormous. Since the Lorimer burst in 2007, researchers had accumulated hundreds of fast radio bursts, developed competing theoretical models, and debated endlessly about what class of object could produce them. Magnetars, which are neutron stars with magnetic fields a trillion times stronger than Earth's, had been among the leading candidates. The simultaneous detection of a radio burst and an X-ray flare from a known magnetar confirmed, at least in principle, that the mechanism existed. The FRB mystery appeared to be, at last, on the verge of resolution. It was not. SGR 1935 plus 2154 is one of roughly 30 known magnetars in the Milky Way. In the years since FRB 200428, astronomers have monitored all of them intensively. Only SGR 1935 plus 2154 has produced a burst of this character, and it has not produced another one at comparable intensity since. The magnetar mechanism explains how a fast radio burst can be generated. It does not explain why this one magnetar produces them, while the others, equally energetic, equally magnetic, equally ancient, remain radio silent. The answer to one question has opened the door to a harder one. The burst from SGR 1935 plus 2154 was thousands of times brighter than any radio emission previously observed from a magnetar in our galaxy. Had it occurred in another galaxy, it would have registered as a weak, fast radio burst in our catalogs, one more unexplained flash from the distant universe. The same physical process capable of producing a signal we can receive from billions of light years away has been firing in our own cosmic backyard, and we watched it happen without fully understanding a single step of the mechanism. The discovery that fast radio bursts can originate from our own galaxy's magnetars did not solve the mystery. It revealed that the mystery was deeper, stranger, and closer to home than anyone had prepared for. Whatever is happening inside SGR 1935 plus 2154 is connected to every unexplained flash we have ever received from the distant universe, and we still don't know what it is. Number 1. The new unknown. In January 2022, astronomer Natasha Hurley-Walker of the Curtin University node of the International Centre for Radio Astronomy Research in Australia published a paper in the journal Nature describing something that did not fit into any existing category in astrophysics. Detected using the Murchison Wide Field Array in the Western Australian desert, the object was designated Gleam XJ 16275 9.5 minus 5 23 50 4.3. It had pulsed intensely for approximately 3 months in 2018, emitting bright bursts of radio energy roughly every 18 minutes before going completely silent. It was, in her own words, a type of object that theorists had not predicted and that existing models could not explain. Pulsars spin in milliseconds to seconds. Magnetars produce irregular outbursts. Fast radio bursts are single events or clusters lasting milliseconds. Nothing in astrophysics emits a regular, bright, coherent radio pulse every 18 minutes, and no mechanism has been proposed that cleanly accounts for it. The energy and coherence of the pulses require the same type of physics that governs neutron stars, but neutron stars do not spin slowly enough to produce 18-minute periods. The object would have to be spinning far too slowly to generate pulses by any known mechanism. It should, in the language of pulsar physics, be beyond the death line, a theoretical boundary past which a neutron star can no longer produce coherent radio emission. In 2023, Hurley-Walker's team published a second paper in Nature describing another object of the same type. GPM-J 1839-10, pulsing every 21 minutes, also in the direction of the galactic center. When researchers searched archival radio data stretching back decades, they found GPM-J 1839-10 had been pulsing for at least 35 years without anyone recognizing what they were seeing. These objects, now called long-period radio transients, have since been detected in multiple surveys around the world, suggesting they are not rare anomalies, but members of a previously invisible population that has been broadcasting across our galaxy throughout the entire history of modern radio astronomy. No model accounts for them. A neutron star spinning this slowly should not be producing coherent radio emission. A white dwarf is a candidate for GPMJ 1839-10's long operational lifetime, but no confirmed white dwarf pulsar has ever been identified at radio frequencies. The precise, repeating nature of the pulses rules out one-time explosive events. The coherence of the emission rules out simple thermal processes. Every class of known astrophysical object has been held up against these sources and found to fall short in at least one critical respect. Researchers have described them explicitly as representing a new class of astronomical object that current theory did not predict and cannot yet explain. For as long as humans have been pointing radio telescopes at the sky, these objects have been pulsing quietly across our galaxy, once every 18 minutes, once every 21 minutes, steady and rhythmic and entirely invisible to us, because nothing in our theoretical framework told us to look for them. We have spent decades cataloging the universe's radio sky, convinced we understood its basic grammar, and the long-period radio transients have revealed that we were reading an incomplete dictionary. The universe contains entire classes of object we do not have names for yet. Broadcasting on schedules we never thought to listen for, in a language we are only now learning exists. If you want to see more videos like this, click the video on screen now and make sure to subscribe.